Okay, so let's get started with this little note on sample space. So the fundamental counting principle, like I mentioned a second ago, this is something that's covered in geometry actually at the end. But dual credit, a bunch of y'all haven't had geometry yet. So let's briefly talk about it. You may want to make notes on the side, on those lines, just since the text is so small, unless you can read the small text. Okay, so what the fundamental counting principle says is that if one event can occur m ways, another can occur n ways, to find out the number of combinations of m and n you have, you just multiply m times n. That's what the fundamental counting principle says. And it can be extended to any number of events occurring in a sequence. So let's say you're wanting to be crazy and figure out how many total meal combinations you could have if you went to Chili's. You were going to go to Chili's every day for a year, and you wanted to eat something different every day. How many days would you have enough combinations to eat something different? So chances are, with all their menu options, yes, you would. But the way you would calculate that, like multiply the number of appetizers times the number of entree. Let's say you're going to get appetizer, entree, and dessert. Figure out how many appetizers they have, how many entrees, how many desserts, and multiply together. And that's how many different outcomes you could possibly have. Now, that's not saying maybe you're eating a different appetizer, but the same entree and dessert. But it's still a different meal because you ate a different appetizer. Anyways, that's what the fundamental counting principle says. So if we look, my clicker will click. Oh, it's turned off. Way to go. There we go. This first example I put on here, it says you want to pick an outfit to wear out of 6 shirts, 3 pairs of pants, and 4 pairs of shoes. You don't care that they match. You're going to wear blue, purple, and yellow, and you don't care. Let's just say you're doing that. And you want to randomly reach in and grab a shirt, grab a pair of pants, grab a pair of shoes, and walk out the door. How many different outfits could you pick? Well, you would just multiply 6 shirts times 3 pairs of pants times 4 pairs of shoes. That gets you 72 different outfits. Now, let's use another example. Let's say we're assigning ID numbers to students. And we have a couple of things we have to do. First, the first digit cannot be a 4 or a 5. Maybe that's reserved for staff or something. I don't know. And then the last digit must be a multiple of 3. How many 5-digit numbers can the school district assign? Well, we want a 5-digit number. So you could start by just putting blanks for each of the 5 digits. And then you just go through each blank and figure out, are there any restrictions? So for the first digit, did I say anything about any restrictions on the first one? Can't be a 4 or a 5. So how many options does that leave me with? 8. So the first digit has 8 options. Did I say anything about the second digit? Nope. So how many options would that be there?
10.
10. What about the third? 10, 10, it's down here. The last digit has to be a multiple of 3. So we got to think, okay, what are our multiples of 3 from 0 to 9? Well, 3, 6, and 9. So how many different options do I have for that place? 3. That's what goes in that blank. And then to figure out the total number of IDs, you can just multiply straight across. You'd get 24,000 ID numbers. So, dual credit, you probably for sure want to hold on to this because I think this is a vocabulary. So keep it somewhere safe. AP, you can do what you want. You can make a paper airplane and throw it nose first into the trash if you wanted to. I mean, it's not in your curriculum, but okay. So let's look at 6.2 and 6.3. That's going to be our goal today, to get through 6.2 and 6.3 together. And then tomorrow we'll spend all day on 6.4. Oh, before I forget, dual credit, when's our next assignment due? Tomorrow at midnight. Don't wait until tomorrow at 9 o'clock to send me a remind. I'm stuck on number 15. I'll get to that in the morning, sorry. Hashtag sorry, not sorry. So we're going to cover all the material for that assignment today. So I would work on it tonight, at least get one run through in the Blackboard so then you can check your answers and see which ones you want to ask questions on if we have time tomorrow. Or if you want to stay for tutoring tomorrow. Or actually, what, I'll do virtual tutoring tomorrow. So, anyways. 6.2, we're going to look at the definition of probability. So what is probability? That's the question we're going to answer. There's actually 3 different approaches to it. We have theoretical, which is like, you have a coin, heads or tails, it's probability 1/2. There's theoretical. There's subjective, where you use your experience and stuff. And then there's relative frequency, or it's also called empirical, where you use past data. You use hard data to look. So we're going to look at those 3 ways. So first is the classical approach, or it's also could be called the theoretical approach. So in a chance experiment that has k outcomes, all of which are equally likely, each individual outcome has the probability of 1 over k. So that's like, again, flipping a coin. You flip a coin, how many outcomes are there? 2, heads or tails. So the probability of getting heads would be 1 over 2. That's all this is saying. So the probability that the event happens is the number of outcomes favorable to E divided by the number of outcomes in your sample space. So in our coin example, heads or tails, heads is favorable. So that'd be 1 on top. Number of outcomes, well, you can get either heads or tails. So 1 over 2. And if we have like a fair die, then I want the probability I roll a 2. Well, that'd be 1 over 6. That's classical probability. So let's say we have a football team that instead of sending the captains out, they just randomly pick a team member to go out to the middle of the field and do the coin toss. So how do we do it here, Riley? Is it the captains go out for the coin toss, or?
Yes, sir.
Captains. I wasn't sure how. Let's say we just pick random. So this week, someone on the offensive line or offensive team will be selected to call the toss. There's 5 interior linemen on the offense. We want to find the probability that L occurs, which means a lineman is picked. So how can I set that probability up?
5 over 11.
5 over 11. There's 5 linemen, 11 total, so 5 over 11 would be your probability. Okay, so now, I don't know why it says 2 coin example. This isn't coins we're dealing with. We're going to roll 2 fair dice. And we're going to observe the sum of their faces. So if we roll a 3 and a 4, 3 plus 4 is 7. That's what we're wanting to look at. So our sample space is all the different possibilities when we roll a pair of dice. We could roll a 1 and a 1, a 1 and a 2, 1 and 3, 1 and 4, all the way to a 6 and 6. So the pair 1, 2 means that 1 is what was on the first dice, 2 was on the second die. So that means our sample space consists of 36 equally likely outcomes. They're fair dice. We didn't weight one side. We didn't dip one die in something to make it heavier. They're just fair dice, like you would get in Monopoly or something. So let's say E is the event that we roll a 6, or that the sum is a 6, I should say. To define event E, so what are all the ways we could roll a 6? So they add up to give you 6. If I had 1 on one die, what would I have to have on the other? 5. So 1 and 5 is 1. What's another? 2 and 4.
3,
3.
4, 2.
4, 2.
5, 1.
5, 1. So that would be our event, that we get one of those options. Which means there's 5 total outcomes that we actually want. What's the probability that E occurs? 5 over 36. That's right. Questions on this example? Just a little study tip on while we're waiting on everyone to finish writing. One thing that I would do as I'm working on my homework, other than having my notes out, also have my formula chart out. That way, I can get used to what all the formulas are on the chart. So on test day, it's not like I'm just staring at it, like, I don't know what that one looks good. I'll use that one. You'll actually know what each formula means on the chart. When I was grading the test, I saw some random formulas written down, and it's like, yeah, no, ain't wrong. Okay, now, let's say we have an archer shooting arrows at a target. If we wanted to calculate the probability of getting a bullseye, we would find the ratio of the area of the interior circle, the inner circle, so our bullseye right here, to the area of the whole target. And that would give us the theoretical probability. But now, let me ask you this. If it was a very experienced archer who competes on the Olympics archery team, they were shooting arrows at our target, would that be the same probability? Would they have the same probability of hitting the bullseye as I would have when I've never shot a bow and arrow? No. So I probably wouldn't be able to hit the target if it was 2 inches in front of my face. Where I could just take the arrow and boom, yay, I hit it. I probably still wouldn't be able to hit it. So our classical approach doesn't work for every situation. It won't work in this case because there's different probabilities. I find it funny though, like you actually, let's say you're trying to throw something, even from a short distance, into the trash can. It seems like when you try, you miss, but then when you just casually chunk it in there, and it's like, oh cow, it just bounced off the wall and bounced right in. I couldn't do that again if I tried, but let's try again. Boom, boom, miss. Yeah.
That's cool.
Yeah. You hit a hole in one, you're like, yeah, I did it.
I hit an eagle last week.
Oh, wow. That's, how many under par?
It's 2.
Two under
It's
par.
2, yeah.
What's a bird?
1.
1, okay. But I guess that all depends on wind speed and the angle you hit the ball and all that. Okay, so let's look at the subjective approach. This is probability that can be interpreted as a personal measure of strength or belief that a particular outcome will occur. So if Tiger Woods was golfing on the same course you were, Stephen, he'd probably hit him way under par compared to what you would, right?
Yes.
Definitely. So that's subjective. His chances of hitting it at a lower par would be higher. So let's say an airline passenger reports the probability of being placed on standby, meaning that she got to the gate or he got to the gate. Oh, wait. Okay. She got to the gate and they said, oh, sorry, we're full. We're going to put you on the standby list. her probability that she thinks is 0.1, so a tenth. She came to this through personal experience and observation of events. So maybe 1 out of 10 times she gets to the gate and they put her on standby. Then she'll say, oh, it's got a 10% shot. But that's subjective. It's based on her experience and maybe a few observations. The problem with this subjective approach, though, is that different people could assign different probabilities to the same outcome based on their experience. Let's remind. No. So it's very subjective. I mean, if you're a stockbroker and you're sitting there and you're, oh, based on my experience, when the market does this, this is about to happen, so I'm going to make this big transaction. But then someone else comes and says, I don't know, you may be careful with that. You're being kind of risky. No, I know what I'm doing. Okay. And then let's say that stock boom drops when the guy expects it to increase. Well, he was wrong. But it's all subjective. Okay, and so the subjective approach isn't the best. It's based on personal experience. The next approach is the relative frequency, or it's also called the empirical approach. Dual credit on your homework and on your test, it's called the empirical approach. It means the same exact thing, it's just called something different. So the probability of event E is denoted by the probability of E. It is defined to be the value approached by the relative frequency of occurrence of E in a very long series of trials. So that this would be like if we stood here and flipped a coin 2,000 times. Overall, we would expect the frequency that we got heads to be 1/2. Relative frequency would be 1/2. If we just flipped it 10 times, it probably won't be close to 1/2. So if the number of trials is quite large, the probability is approximately equal to the number of times E occurs divided by the number of trials that we actually have. So the number of times E occurs divided by the actual number of trials. Okay, so we're actually, for these next two graphs, going to use that coin example that I just talked about. Let's say we flip a coin and we record the relative frequency of getting heads. So when the number of coin flips is small, notice how much variability there is in our graph. Skyrockets and then falls, and then it's just zigzagging all over the place. Almost looks like a stock market chart. There's a lot of variability in the relative frequency of heads, as shown in the graph. What do you notice eventually happens though? So at first we're jumping all over the place,
Kind of stabilized.
and then it starts stabilizing. Is it totally stable though when we get out to 50 trials?
It's just like up and down.
No, it's still just kind of up and down. It's just a little bit slower rise and fall. But now, let's say we flip it 1,000 times. What do you notice now? It's a lot closer to 0.5. It really starts stabilizing and gets really close to our theoretical probability. It does, but notice how close it's staying to 0.5. Like 0.4 is all the way down here. Notice how close we've stayed to 0.5. So think of it like another way to think of this is your grade point average, or not your grade point average, your actual grade. What happens when there's very few grades and you put a new one in? It affects it more. You'll sit there and see all these spikes and drops and going all over the place, but then what happens as the 9 weeks goes on? It starts flattening out and kind of staying constant unless you do something that really makes it drop. So it's kind of funny. I'll say that in AP we're getting to that point. We're getting where it's just kind of starting to flatten out. I mean, there were some good grades and not so good grades, but then overall it barely changed your final average. You're getting to that point where it just starts flattening out. Dual credit, we just had our first test. We've only had 8 assignments, so it's still kind of up and down, up and down, up and down. Now what I will say now that we've had our first test, every test after, your test weight becomes more and more. So right now, when you look at your grade, half of your grade is from the test, that one test. The other half is from your homework. When we take test 2, 2/3 of your grade will be from the test, 1/3 from homework. Test 3, that goes up to 75% of your grade. So that's just how college is, though. Most of your grade is test. Anyways, back on topic. So in many real-life processes and chance experiments, the probability of a certain outcome or event is unknown. But nevertheless, the probability can be estimated reasonably well from observation. I mean, if we're being totally honest, meteorologists use this all the time. 10% chance of rain today. Well, it's not that 10% of the day it's going to rain. It's just in 10% of the days, with our same exact conditions, it rained. So that's why there's a 10% chance of rain. What's that?
That makes sense. I've always wondered how you figure it out. That makes a lot of sense.
Yep, under these same exact conditions. That's why, like, if you have a real strong cold front, they throw it to 100%. Because when those real strong cold fronts come through, they clash with our Gulf air and boom, thunderstorms, and then it blows through. So that's how they do it. They look at historically, these are our conditions, what historically happens. Oh, 50% of the days it rains, so 50% chance of rain. Okay, so law of law of large numbers tells us that as the number of repetitions of a chance experiment increases, the chance that a relative frequency of occurrence for an event will differ from the true probability by more than any very small number approaches zero. So that's just a bunch of gobbledygook. In other words, let's put it into language that we can actually understand. After a large number of trials, the relative frequency approaches the true probability. So that's why on our heads and tails graph, once we started getting out past 1,000, it started getting really close to 0.5 and then just stayed there. Maybe went a little above, a little below, but it pretty much stayed at 0.5. Let's see some writing. Oh, wrong one. There we go. Okay, so relative frequency, again, let's say we roll a die, a fair die now. So we're not going to do coins, we're going to do die. We would like to investigate the probability of getting a 1 for the up face of the die. So rolling a 1, essentially. The die was rolled, and after each roll, we recorded what we got. And then the proportion of times that a 1 was rolled, we calculated that and plotted the point. So when we start off at first, notice how much our relative frequency jumps. Jumps, then falls, then jumps. And then eventually we start kind of evening out where? Around 1/6, which is our theoretical probability. And that's if we roll it 2,000 times. Now, we look at this graph and we're like, that's kind of cool. But I don't know the law of large numbers. I forgot what Mr. Schultz said. So I've got 2 free hours. Let's roll this die 2,000 more times to see if it happens again. So we do. We roll it 2,000 more times. And then, sure enough, what happens again? It evens out at 1/6 again. And then you're like, oh yeah, that's that law of large numbers thing. It approaches the theoretical probability. I remember now that I've wasted 5 hours. But then you wouldn't forget it. Okay, so that's just showing that the relative frequency or empirical approach eventually gets back to the classical approach. So now, when will we use each of these? If we have if we're thrown a situation and we have to figure out which approach to take, how can we decide which one would be right? So we would pick the classical approach if the experiment can be described with equally likely outcomes. So rolling a pair of dice, drawing a card from a deck, that's not a stacked deck. Flipping a coin. Stuff like that, the classical approach would work. They have equally likely outcomes.
Would they both, like, do they both work for each other, or do they have to be in certain scenarios? Or like, is one just like more helpful than the other in certain situations? Both of you.
One tends to be more helpful than the other.
I got you.
I mean, like flipping a coin, for instance, you could use relative frequency, but then you'd have to sit there and flip it a bunch of times to see what it historically would be. To where the classical approach already tells you it should be a half.
Okay.
Does that make sense?
Yes, sir, that's understandable.
Subjective, that's what we gotta kind of be careful with. These probabilities represent an individual's judgment based on facts combined with personal evaluation of other information. So this one, the best one that I can think of for this one is just the stock market. You don't know exactly what's going to happen, but based on how you see the data, you can act on it. That's subjective to your opinion. I may look at it and say, I need to sell this stock. Justine may look at it and say, sell? I think I want to buy the stock. I think it's about to do this. And so, yeah, that's subjective. Relative frequency is an estimate based on the accumulation of experimental results. This estimate presumes a replicable chance experiment. So where relative frequency comes in is like, for instance, let's say you're selling mixers, like the KitchenAid stand mixers, and historically, you look at the data and you're like, yeah, 20% of these have come back to us defective. That would be relative frequency. You look at all your sales and then say, okay, 20% have came back defective. So this one has approximately a 20% chance of being defective. Now, obviously, if you're a company, that's like insanely high and you would not want to sell that. You wouldn't want to sell that, but anyways, that's relative frequency, or also called the empirical approach. So questions on 6.2.
I get some water on
No questions on 6.2? Okay, 6.3, moving onwards. So we're going to look at basic properties of probability. So there's 4 basic properties that we're going to talk about. The first one discusses what values we could have for probability. So if we have an event, the probability must be between 0 and 1. It can be 0 and it can be 1, but it's got to at least be in between that range. You can't have a negative 33% chance of rain or a 150% chance of rain. It's got to be between 0 and 1. Now, if we took the probability of getting something in the sample space, that would have to be 1. If I'm flipping a coin, I'm not going to say I mean, it's heads or tails. That's now you could get technical and say, it can land on its side, but that's such a slim probability. For our case, we're going to say that that probability is pretty much non-existent. It's going to be heads or tails. But if I went up to you and said, what's the probability of getting heads or tails when I flip this coin, you're going to look at me and say, 100%. You're going to get one of them. So that probability has to be 1. Another one is the addition property for disjoint events. Anyone remember from Friday what disjoint meant? Disjoint means they have nothing in common. So the probability that E or F happens if they're disjoint would just be the probability of E plus the probability of F. Now, if they have something in common, like we're going to learn later this week, we can't just add them. There's going to be something else we have to do to them. But if they're disjoint, meaning they have nothing in common, then that would be their probability. And then we have the complement. So for any event, the probability of that event plus the probability of not getting that event has to be 1. Questions on these properties? Okay, let's see what happens when we have equally likely outcomes. So let's say we have an experiment that can result in any one of n possible outcomes. We're going to denote the simple events, which remember a simple event is getting only one outcome. We're going to denote the simple events by O sub 1, O sub 2, all the way to O sub n. If these simple events are equally likely to occur, then the probability of O sub 1 equals 1 over n. Probability of O sub 2 equals 1 over n. All the way to the end, probability of O sub n is equal to 1 over n. And if we have any event E, the probability that E occurs is the number of outcomes in E divided by capital N. Okay, so let's look at another die example. So suppose we roll a 6-sided die once. Let E be the event that you roll an even number. Find the probability of rolling an even number. Well, what even numbers are on the die? 2, 4, and 6. So how many outcomes do we actually want? 3 out of how many total? 6. So that's our probability. 3 over 6. Now, typically you would reduce this. I did not here just to illustrate that the 3 is the number of outcomes in E. We have a 2, a 4, or a 6. And the 6 is the total number of outcomes you could have. So N. Anyone else still need this slide? Okay, let's look at a playing card example. So consider the experiment consisting of randomly picking a card from an ordinary deck of playing cards. So a 52 card deck, we're throwing the jokers out. Let A stand for the event that the card chosen is a king. Why they chose A, I have no clue. Yes. I would have chosen K for king. The sample space is given by, well, before I show it, what are all, well, I'm not going to say what are all, because I don't want to be here all day. Can you think of a way to summarize what you could get when you draw a deck of cards, from a deck of cards? Well, there's an ace, king, queen, jack, all the way down to a 2, right? And then what different suits do we have? Clubs, hearts, diamonds, and spades. So we're going to summarize that using this right here. So ace of clubs, king of clubs, all the way down to 2 of clubs. Then we start again, ace of hearts, king of hearts, all the way down to 2 of hearts. Then I get tired of writing king, so I just abbreviate ace of diamonds to 2 of diamonds, and then ace of clubs down to 2 of clubs. So there's 52 equally likely outcomes here. Now, while y'all try to get that written down, I can't remember when it happened, but I remember reading this story that a casino actually got busted for using a stacked deck of cards. Actually, 2 or 3 casinos got busted for stacking the deck of cards in their favor. So they, instead of playing with a fair deck, they would stack it to where they could pretty much guarantee that you would lose all your money. Well, the way they found it, they had these card sharks come in that would try to predict what you should get. And these are the people that, in normal casinos, they get escorted out because the casinos are losing money from them because they're able to predict how much they should bet based on what cards they've seen. So they send in these people undercover, and they can't predict anything at these 2 or 3 casinos. Like they're losing all their money. In a normal situation, they could almost guarantee you what's about to come next. And here they couldn't. They were like, this is making no sense. So they actually investigated and found that those few casinos had modified the deck of cards and taken some out and added others in. Yeah, they didn't do that again. They actually they came in, seized all their cards, and the casino had to pay not only fines for not being fair, but then they also had to buy all new decks of fair playing cards. So, I guess it kind of comes on both ends. It's bad. They don't like the card counters because they lose money, but when they try to prevent that happening, then they get fined for it. So, anyways, so we have our sample space written down, hopefully. Let's define our event A. So what is A? Getting a king. So what are all the different ways we could draw a king here?
In every suit.
Yep, one in every suit, right? King of spades, king of hearts, king of diamonds, king of clubs. So our event has 4 outcomes in it. So what's the probability then of getting a king? Four out of 52. I'm sorry. I thought somebody did, so I wasn't sure. So the probability of A is 4 over 52, which reduces to 1 over 13. Okay, questions on this example?
Oh, okay. Thank you.
Now, these next 2 examples that we're about to do are actually important because we're going to use these 2 examples, these next 2, for our big final example at the end. I'll say big, like it's a big example. It's really not, but anyways, they're going to be used. When we get to that last example, instead of recalculating everything, we're going to say, look back at these 2 for your calculations. Okay, so let's look at another dice example. So let's say we want to figure out the probability of rolling a pair of dice and getting the sum of 7. Well, we're going to have our normal pairs, 1, 1, 1, 2, 1, 3, all the way to 6, 6. That's not going to change. If we roll 2 dice, this will always be the sample space. And there's going to be 36 equally likely outcomes. So now I want to roll a pair that adds to 7. So what are my different options that add up to give me 7? 1, 6, 2, 5, 3, 4, 4, 3, 5, 2, and 6, 1. That's right. So our event E is given by those 6 possibilities. In case you didn't know this, getting a sum of 7 is actually the most common sum when you roll a pair of dice. It's the only one that can be gotten to 6 ways. So what would our probability be of getting a sum of 7? Well, there's 6 outcomes that we want. How many total could we get? 36, so the probability would be 6 over 36. Now, typically we would reduce it, but for now we're going to leave it as 6 over 36 because we want to use this answer at the end. We're going to need this example on the next page. Okay, so we're going to keep the same scenario, except this time we don't want it to add to 7. We want it to add to 11. So we would still have the same sample space. 1, 1, 1, 2, all the way up to 6, 6. Which means there's 36 equally likely outcomes. How many ways are there, though, or what are the ways to roll a sum of 11? 5, 6, 6, 5. Oh, sorry. So since there's 2 outcomes that we want, what would the probability be of getting a sum of 11? 2 out of 36. Good. This time we did reduce it. Okay, last topic for today. The addition rule for mutually exclusive events. Yes. You know, like on this one? So, what I will say is read the problem and it'll tell you, usually you will put it in decimal form. What I'll also say is on y'all's homework, I could not get Blackboard to save my life. Let y'all enter an answer in fraction form. So, I had to put everything in decimal form. So, even though on your paper assignment it'll say put it as a fraction, Blackboard, put it as a decimal. You're welcome. Yeah, I spent 30 minutes like, can I do it this way? No. Can I do it that way? No. Okay, let me Google. Google doesn't have an answer. They can just enter it as a decimal. I'm tired of looking. I got other stuff to do, I'm sorry. So, if Google doesn't know how to do it, there's no hope. Okay, addition rule for mutually exclusive events. So if events E sub 1, E sub 2, all the way to E sub k are disjoint, meaning they're mutually exclusive and have nothing in common, then the probability that E1 or E2 or E3 all the way to E sub k, EK, is just the sum of their probabilities. So this is that last formula on page 11. So while y'all finish writing that, I'll talk about that top sentence on the next page. So in other words, any of these K disjoint events, the probability that any of them occur is just the sum of each individual probability. Think of it like we're rolling a die. You can't roll a 2 and a 4 on a single die at the same time. So those are disjoint events. Okay, let's look at this car sales example. So a large auto center sells cars made by many different manufacturers. 3 of these are a Honda, a Nissan, and a Toyota. Consider a chance experiment that consists of observing the make of the next car sold. Suppose that the probability of selling a Honda is 0.25. Probability of selling a Nissan is 0.18. And the probability of selling a Toyota is 0.14. Are these disjoint events? Can I sell a Honda Camry? No. Toyota's the only one that makes Camrys. Can I sell a Toyota Civic? No. We're not putting the Civic motor in the Toyota or vice versa. Toyota motor in the Civic. We're not doing that. So are these disjoint? Yes. How would I find the probability of selling the Honda or the Nissan or the Toyota? What did my property tell me on the previous page? Add them all together. That's right. We can add them all up. So if I add them all up, 0.25 plus 0.18 plus 0.14, I get 0.57. Okay, now, how would I find the probability of selling neither of these? None of these. So, not Honda or Toyota or Nissan. 1 minus 0.57, good. So the probability that I could sell them is 0.57. The probability that I can't sell any of them would be 1 minus that probability. That goes back to our complement rule. And the fourth property, I think it's the fourth. Yes, Nate.
Do you have to say word after every letter or just the last letter?
What do you mean?
Like instead of H or N or T, you say H N or T?
No.
It has to be H or N.
Yeah. And that just deals with like probability terminology. Yeah. Because instead of saying the word or, you traditionally would use the union symbol, the thing that looks like a U, which we talked about on Friday. And then for and, you would use, it's called a cap. Basically, it looks like that U symbol but flipped. And so if it was and, it'd be H and with the little cap in and T. So that's why we have to really specify here. Okay, so probability would be 0.43. 1 minus 0.57 is 0.43. Okay, last example. Remember I said this one right here uses the 2 on the previous page. So consider the experiment where we roll 2 fair dice and we look at the sum. E is the event that the sum is a 7. F is the event that the sum is 11. Okay. What did we say the probability of E was on the previous page? Getting a sum of 7, what was that probability? 6 over 36. What about getting a sum of 11? 2 over 36. We'll go with 2 over 36 for now. Okay, let me ask you this. Can I roll a pair of dice and get both a 7 and an 11 on that one roll? No. So would these be disjoint events? Yes. So since they're disjoint events, they have nothing in common. We could simply add the 2 probabilities together. And that would give us the probability of getting a sum of 7 or a sum of 11. So 6 out of 36 plus 2 out of 36 equals 8 out of 36, and then we reduce it down to 2 over 9, which is approximately 0.2222. Okay, questions on this example? Or on anything we've done today? For the disjoint, are you saying, could I say, like, instead of E or F, say E and F?
Yeah, like for non-disjoint.
Oh, for non-disjoint, so things that do have in common, then yes, you would use it. But, well, then you want, if you use an and, you want to look for what they have in common.
That's so
Then that would be your answer.
So like, if there was one thing in common, we gained out.
Yes.